Hi guys, welcome back. We have defined the adjoint for a given bounded linear transformation between two Hilbert spaces, and we have just completed a proof of a rather lengthy theorem that summarized all the key properties of the adjoint. There was one part to it. This was, I think, the fifth part, which was a statement about continuity of a map that sends a bounded linear transformation to its adjoint in three different topologies. We prove the statement about the uniform and the weak topology, which is just fancy talk for saying what happens to a uniformly and weakly convergent sequence if you look at the sequence formed out of the adjoints. Right? There was the statement that in general this map is not continuous in the strong operator topology, and while we were going through the proof I said we will address the strong operator topology with an example, and that's what I will be doing now. So let's look at Hilbert space H, the square summable sequences over, say, complex number field, and then we need a operator a sub n that we encountered in a previous example right before we defined the adjoint. This was the right shift but executed n times. So instead of just having one zero here, you have n zeros out front, and then the whole train is just moved to the right. Okay, so unlike the left shift, you're not losing any information with the right shift, no matter how many times you execute it. All right, so now let's we will compute the adjoint of this right shift, and maybe it's not so surprising what comes out there. So then for any x in y, right, so this is a good exercise given some Hilbert space and some operator, compute its adjoint. Okay, it can be pretty tricky, but this one is not tricky. So now here we have to use the definition of the inner product on L2. Okay, this is very much like the dot product on the n-fold copy of the complex plane, but the sum goes all the way to infinity. So we have kth entry of an acting on x, and then yk bar. But an xk, this is, you can read off from up here what it is. Well, it only gets active at the n plus first slot, and then the information that you get is the entry x sub k minus n, right? Because it starts here with 1, then 2. It doesn't start with n plus 1 and n plus 2, it starts with 1. All right, so you have this, then yk bar just stays as is. And now you can just subtract n terms here in the index, so just relabel your indices however you do this, and then this gives you xk, yk plus n, and then the bar on top. Yeah, but now if you remember what the left shift does, the left shift moves everything to the left, but it erases information from the sequence. So if you apply it once, the image sequence would not start with x1, but it would start with x2, then x3, x4, right? And if you do it n times, you start with x sub n plus 1, then x sub n plus 2, but the first n terms are all gone. And that's precisely what's written here. This is inner product x with Sn acting on y. All right, so this shows that the adjoint of the right shift executed n times is the left shift executed n times. All right? Yeah, but we know a thing or two about these guys, in particular when n goes to infinity, for all n in n, okay? But we know, this was an example, before this section on the adjoint started, we know that Sn goes to the zero linear transformation strongly as n goes to infinity. However, remember the adjoint of the adjoint is itself. So if you want to have now the adjoint of Sn, well, that would be adjoint of an. So this is just an, all right? We know that an does not converge. Does not converge strongly to 0, right? So although you started with a strongly convergent sequence, those SNs, they go strongly to 0. The sequence built out of the adjoints, SN stars, does not converge strongly to 0. Hence, that's precisely what it means to say that this map T going to the adjoint is in general not continuous in the strong operator topology. Okay, excellent. So this really now closes the proof of that theorem about properties of the adjoint. All right, so now what we will do is we will give meaning to some special bounded linear transformations, and the question is always, how does a linear transformation behave sort of in response to the adjoint? Okay, so there will be now here 3 types of actually linear operators. Well, two will be for operators, 1 will be for linear transformations. So a bounded linear operator T in LH on a Hilbert space H, on a Hilbert space H. So everything, again, keep this in mind whenever you're dealing with adjoints here. This is in the Hilbert space case, because the defining equation for the adjoint, that you can move the action of T from one entry in the inner product to the other entry, it needs an inner product, so there's no meaning for an adjoint in a Banach space, right? On a Hilbert space H is called normal. So maybe you remember from linear algebra what normal matrices are, and well, they are precisely what I write down here. So a normal matrix, you look at the matrix which is the conjugate transpose of the matrix, and you multiply it with the original matrix once from the left and once from the right. And then if that product matches, then you call it a normal matrix. And that's precisely what's written here, but for bounded linear operators on infinite dimensional Hilbert spaces. Okay? And that's probably well-known self-adjoints in linear algebra. I would call this Hermitian, but not here in functional analysis, because Hermitian for me is something else that we will actually not discuss in this class. It has to do with unbounded operators. But here we will call self-adjoint if, well, the operator is equal to its own adjoint, which can happen. It did not happen in this example right before the definition, because one was right shift and the other one was left shift, right? So they're not the same. Moreover, if H1 and H2 are 2 Hilbert spaces, we call a bounded linear transformation U from H1 to H2, we call it unitary. So actually that concept already occurred when we talked about Hilbert space isomorphisms, and that's precisely what I write out here. But there we didn't have the notion of an adjoint, right? So it was defined slightly differently, but actually it turns out that is equivalent to what is defined here, and we will discuss it. Okay, so we call a bounded linear transformation unitary if you compose the transformation with its adjoint, once from the left, once from the right, and you get the identities on the respective Hilbert spaces. These are the unitary ones. Okay. Again, in linear algebra, these would be unitary matrices, or if you are if you're playing around with matrices with real entries, those are orthogonal matrices. Okay, good. Let's do some example here before we develop theory. So example, having normal self-adjoint and unitary operators, this really is a good thing to have, but in turn it means that these operators, they have to satisfy, they have to have some built-in symmetries, which is great when you have it, but it's I would say more the exception than the norm. So okay. Anyways, let T be bounded linear operator on small L2 denote the multiplication operator. Oh yeah, so this was in the first week. Multiplication operator. Meaning given a sequence of complex numbers Tn, bounded sequence, so element in L infinity, the multiplication operator acts as follows. Well, it multiplies each entry of a given sequence by the corresponding element in that sequence of the Tn's. So it is sent to T1 x1, T2 x2, T3 x3, on and on. Okay, we convinced ourselves this is a bounded linear operator. The operator norm of the multiplication operator is precisely the infinity norm of the sequence that you multiply with. All right. So now then let's compute the adjoint, and then let's see if we are playing around with a normal self-adjoint or maybe a unitary operator. So, well, maybe the result is not so surprising because it will depend on the properties with the numbers that you multiply with, right? So let's write this out. So it is Txn, because that's the inner product on L2 after all, we had in the last example. Now this is, by definition, you can read it up there, T sub small n xn, because the nth entry is just Tn xn. That's what I'm using here, or equivalently for there. And then yn bar, and then here a little bit of trickery. So the complex conjugate of a number is the number itself. So I put a bar here, a yn, and then another bar on top. All right. And this you can do because you're working here with scalars, everything is commutative. Okay, so what this tells us is the following. So it says that T is self-adjoint. Well, how can this thing only be self-adjoint? Well, remember, this here on the right would be X, and then Y, and then, well, something here out front, right? T adjoint, to be precise. But here what we're currently seeing is that the action of T, of the adjoint on Y is just written here. So I put the yellow bubble above the bar of the Tn, right? So it is multiplication, but it is multiplication with complex conjugate T's, right? So x2, that is the adjoint. T1 bar, x1, T2 bar, x2, and on and on and on, right? So self-adjoint would then only happen if the tk bars are equal to tk, and that precisely happens when you're dealing with real t's, right? So t is self-adjoint if and only if tn are real for all n. And unitary if and only if, well, you have to compute now, of course, that these products, they're still up there. You gotta multiply the adjoint with u itself and u adjoint, but that maybe you can do in your head. So if t star, how does it do? Well, it will send me, so the first case is here in green, then I have to multiply that green thing again with t, so it would give me a t1 complex conjugate square here, x1, then t2 complex conjugate square, x2, and then on, right? And that thing is equal to the original sequence precisely when all those tn's in complex modulus are equal to 1, right? So we have that thing is unitary if and only if Tn is equal to 1. Notice, by the way, I computed up here in red Tt star, but if you do it the other way around, you get precisely the same result. Okay. So we have this. However, note that, that's what I just said, you get the same result if you do it the other way around. Note that T is normal for any Tn in L infinity n. Okay? Good. So this multiplication operator is great because it has nice symmetries. All right. Good. Now, moving ahead, I will now derive some easy properties how you can check for self-adjointness. Well, although those properties, to be frank, they are more theoretical interest rather than practical interest. But we will have one for the self-adjoint one, and we will have one for the unitary ones. Okay. I bet the self-adjoint one you have seen at least in linear algebra, and that thing generalizes here to our infinite dimensional setup. So here we go. Let T be bounded linear operator. T be a bounded linear operator on, now this is crucial, and you will see why in the proof, on a complex Hilbert space. So the underlying scalar field has to be the complex number field. Over the real number field, this will fall apart. It's not true. Then T is self-adjoint if and only if all these inner products here, Txx, are real for all vectors in the Hilbert space. Okay, that's the statement. Proof. Well, there's one direction which is super easy, namely self-adjointness of T implies, well, Tx comma x is, by the yellow box, x T star x, which is, well, because self-adjoint, x Tx, and then you use the property of the inner product. You can swap the order at the cost of complex conjugate bar. And this holds true for all vectors x. So what you have here is you have a general complex number which is equal to its own complex conjugate, right? And that means that complex number has to be real. Okay. And so Txx real. Okay, that's the easy one. Now conversely, there we have to work a bit harder. For any x, y in H, well, Tx plus y, x plus y, and here, by the way, in the first, that first direction did not use at all that you are in a complex Hilbert space. That is valid also in a real Hilbert space. But now the second one, the other direction, is only valid if you are with a complex number field. So we have here a few things. So linearity of T and the linearity of the inner product in the first vector allows me to chop this up here in 4 pieces. We have Txy plus Tyx plus Tyy. Okay. Now, by assumption, currently we're doing T, the inner product real implies self-adjointness. So by this assumption, you know that this guy is real, this guy is real, and this guy is real, right? So that means, well, because you're working over a field, and that's closed with respect to addition here. This means simply that these two terms that I didn't underline with yellow also have to be real. So txy plus tyx real for all xy in the Hilbert space. All right. Likewise, and now you see why I need that we are in a complex setting here, because I need the imaginary unit, right? So that thing should be contained in my underlying scalar field, and that's, well, not happening if you're over the real number field. Okay. Now you do the same thing with, instead x plus y, you do it with x plus iy. Okay, so then be careful now, because the iy will appear in the second vector, and in that one the inner product is only conjugate linear. All right, so but if you do it carefully, you get a minus I here, then a plus I, and then the last term is the same because it gets an I from the first vector out and a negative I from the second. I times minus I is plus 1. All right, then similar logic by assumption, this is real, and this is real, right? Hence again, what is in the middle has to be real. It has minus I txy plus I tyx real for all xy in H. Okay, excellent. In summary, what we have proven is the following. For all xy in H, let's write it like this. Well, if a quantity is real, then it's equal to its complex conjugate. So that's what I'm writing out now. Txy bar plus tyx bar is equal to txy plus tyx, and then you do it for the second thing too, but there's these i's, so you have to be careful with the signs, because complex conjugate of imaginary unit is minus the imaginary unit. So here will be I txy and the bar only over the inner product, not the I, and then here similarly tyx, and then minus I txy plus I tyx. Okay, so now you have these two equations. What you can do, for instance, you can multiply the first line by an imaginary unit and add it to the second line. If you do this, these two guys here will go out, and also these two guys go out, and the remaining ones, they add up. There will be a factor of 2i in front of each that you can divide out. So what you get is txy complex conjugate is equal to tyx, right? Thus, using the property of the inner product, getting rid of the complex conjugate bar, you can swap the vectors, and then you have tyx, right? And this holds for all xy in H. Yeah, but then you're done, right? Because this one you can move here with a complex conjugate, not complex conjugate, with an adjoint on top, and then you have y tx inner product is the same as y t star x for all y and x, and that just choose your vector appropriately, right, as we did it before when we showed that this property defines the adjoint uniquely. You get the self-adjointness tt star. Okay, good. This completes the proof of this theorem. It's more of theoretical interest because, I mean, in applications you will not be able to check in general that all these inner products here are real, right? I mean, you have to evaluate them on all vectors in your Hilbert space, which is usually hopeless. Okay, but we need this for theoretical purposes. Okay, I will state the the similar test for the unitary ones, but we will prove this in the next video. So a linear transformation U between two Hilbert spaces H1 and H2 obeys, so each one here comes with its own inner product, so it's really Hi with an inner product that is indexed by I. It obeys U star U is IH1 if and only if ux2 is equal to x1 for all x in H1. This should not come as a surprise, at least from linear algebra, because the unitary or orthogonal transformations, they have geometrical meaning in that, for instance, they correspond to rotations, and rotations are isometries. That's precisely what this property says here, that U is an isometry, right? And moreover, such a U is unitary if and only if it is, well, surjective or onto it, which is the same. So the range of U is equal to H2. Okay, so this we will prove in the next video, and then we will after that we will look at projections. In fact, defining projections for the first time, although you already might know what these are. And once we've studied them, we will finally understand why back in chapter 2 we had a result called the projection lemma. It prepared the proof of the Riesz representation theorem. This was about, you have a closed subspace, then you can complement it with its orthogonal complement. Remember, complementary subspaces we discussed in the end of that section where we had a closed graph theorem. So that, having then some understanding what projections are, then the name will be clear why we call this projection lemma back in chapter 2. Okay, that's more or less the plan. I'll see you in the next video.